Thank you for introduction. Good afternoon, everyone. My name is Yumi Hayashi from Toshiba. The title of my presentation is Investigation of Hydrogen Spatial Distribution During Smoldering Fire in Capacitive MEMS Hydrogen Sensor using PT thin film. This is the outline of my talk. As an introduction, I'd like to talk about the smoldering fire detection and our previous work on hydrogen sensors. Following objectives of this study, I will explain new capacity MEMS hydrogen sensor that we propose. I will then explain the experimental investigating the spatial distribution of hydrogen in smoldering fire. I will conclude with a summary of my talk. This figure shows the causes of death of building fires. As you can see, CO poisoning and asphyxia is a leading cause of death. CO is known to be generated by smoldering fire. This table shows requirement for smoldering fire detection and conventional fire alarms. There is a little heat output in smoldering fire because there is a little flame, making them difficult to detect with conventional heat detection method. Smoke detection methods also have issue of false detection caused by steam or dust. Also, alarm location can delay response smoke and CO detection method. We can therefore see that detecting smoldering fire with conventional fire alarm is difficult. This image shows a smoldering fire that generates CO. When fabric or wood in items such as sofa, clothes, or furniture burn incompletely, CO and hydrogen are generated as shown in this equation. This figure shows specific weight of air, CO, and hydrogen. CO has nearly the same specific weight as air, but hydrogen is lighter, so hydrogen will diffuse upwards. Therefore, it is easier to detect hydrogen by installing a hydrogen sensor on the room's ceiling. We have previously succeeded in using our hydrogen sensor to detect hydrogen generated in the smoldering fire. This is the image of the experiment room. The hydrogen sensor module was installed on the ceiling at the height of 3 meters away from the cotton fire source, as shown in this picture. The installed wireless smart sensor module is equipped with a temperature humidity sensor, detector circuit, and microcomputer. And the hydrogen sensor chip was attached to it. They are a result of the gas chromatography analysis during fire experiment. At the same time as CO, extremely slow amount of hydrogen is generated. This is the response of temperature and humidity sensor and the hydrogen sensor. You can see that hydrogen sensor response after ignition and the response return to the exhaust and fan start. I'd like to explain our capacity MEMS hydrogen sensor that was used in the fire experiment on the previous page. This is the cross-sectional image of our hydrogen sensor. The sensor consists of actuators, membrane, and fixed electrode. The sensing film was formed on the actuators. The film expand or contract by absorbing or dissolving hydrogen. The resulting strain actuates the membrane upward and downward, changing the capacitance between the electrode. There is an issue using this hydrogen sensor to detect ppm order of hydrogen. Approaching hydrogen is dissociated by catalyst and absorbed in the hydrogen sensing film. But at the same time, oxide on the surface of the sensing film it is reduced by hydrogen and dissolved. The film stress, the sensing film changes in the tensile direction due to the oxide reduction, and in the compressing direction due to hydrogen absorption. Because these reactions occur simultaneously, they cancel each other out, resulting low sensitivity. As a result, this hydrogen sensing film easily affected oxygen in the air, making it difficult to accurately derive the hydrogen concentration. Therefore, in this study, we propose a new sensing film structure that is less affected by oxygen in the air. Furthermore, we investigate the spatial distribution of hydrogen generated during smoldering fire experiment using a new capacitive MEMS hydrogen sensor. I'd like to explain the new capacitive MEMS hydrogen sensor that we propose. The proposed capacitive MEMS hydrogen sensor uses PT thin film as hydrogen sensing film and covers it the oxygen control film. I will explain the response mechanism by comparing the presence and absence of oxygen control film. Without oxygen control film, approaching hydrogen reduces PT oxide, but at the same time, oxidation of the PT in the air progresses, resulting in the oxide remaining. On the other hand, when oxygen control film is present, oxygen in the air is dissolved on the SiO2 surface. And hydrogen passes through the SiO2 and reduces the PT oxide. In this way, by using a sensing film with a structure of PT and SiO2, the phenomenon of PT oxide being reduced by hydrogen can be monitored. Next, I will explain the operating principle. In the air, there is PT oxide, and the PT film stress is tensile. In hydrogen-containing atmosphere, the reduction of PT oxide is progressed, and the tensile stress of PT thin film becomes even larger. As a result, the actuator laps more. The gap between the electrodes becomes larger and the capacitance decreases. We evaluated whether oxygen control film can block intrusion of oxygen from the air by measuring the change in PT resistance. As shown in this table, the resistance decreases when PT oxide is reduced in the hydrogen-containing atmosphere. To evaluate resistance change, we use the resistance evaluation sample of MEMS structure like this. Without SiO2, the resistance decreases as the hydrogen concentration increases, but the slope is small. On the other hand, with SiO2, the slope becomes larger, confirming the sensitivity increased. Therefore, it is confirmed that SiO2 suppresses the oxidation of PT by oxygen in the air, and the reduction of PT oxide by hydrogen becomes dominant, thereby improving sensitivity. To confirm whether the reduction of PT oxide actually proceeds through SiO2, XPS analysis was performed before and after hydrogen exposure to evaluate PT oxide presence. Analysis was performed as follows. First, annealing was performed 100 degrees C to promote the PT oxidation. Hydrogen exposure was performed by exposing the sample to about 1,000 ppm hydrogen for 30 minutes. XPS analysis was performed before and after hydrogen exposure. A blanket film sample used for the analysis like this. This figure shows the XPS curve. Before hydrogen exposure, red line, the curve shifted to the left compared to the PT metal reference. The curve after hydrogen exposure overlapped blue line, overlapped exactly with the PT metal difference indicating the absence of PT oxide. From the results, it was confirmed that hydrogen exposure promotes the reduction of PT oxide through SiO2. Here we confirmed the hydrogen response of the new capacitive hydrogen sensor that uses PT and SiO2 as sensing film. As the figure shows, capacitance depends on the hydrogen concentration. Next, let's see the result of a smoldering fire experiment. Now we will explain the experimental procedure to investigate the spatial distribution of hydrogen caused by smoldering fire. As shown here, cotton fire source was placed in the center of the laboratory. 7 hydrogen sensors modules were installed in the grid pattern horizontally and vertically from the fire source. Gas for gas analysis was collected on the ceiling 3 meters away. The evaluation items temperature, humidity, and the response of hydrogen sensor. The sensor module was placed in the enclosure to protect heat and salt. The sensor was mounted facing downward towards the fire source. This figure shows the hydrogen response at each position. The horizontal axis shows the time from ignition. The 0.5 U sensor responded after about 1 minute, followed by these 2 sensors on the ceiling. These images show the hydrogen concentration distribution at each time. The response of the sensors on the ceiling did not decrease until exhaust, indicating the hydrogen remained on the ceiling. On the other hand, the sensor in the middle row began to respond after fire was extinguished. And the sensor in the lower row barely responded. These results indicate that the hydrogen generated a smoldering fire remained near the ceiling. The gas chromatography analysis indicated that the 80 ppm hydrogen, which is much well with the response of 3U hydrogen sensor. This concludes my talk. Thank you very much.